Another example here, this one to do with the magnetic field generated by current. So let's read. A 120 amp current flows through a wire. A 1 Coulomb charge moves directly towards the wire as pictured at a speed of 5 meters per second. What is the magnetic force felt on the charge when it is 0.3 meters from the infinite wire? Now, there's a few keywords just by reading that we should probably focus on. This bolded magnetic force is what we're looking for, and there's not too many equations that can get us to this magnetic force value, and so that should help you figure out what we need. And also this infinite wire is more keywords or hints to look at a very specific equation, and in this case it's going to be the magnetic field generated by an infinite wire. If we're trying to, let's say, look at the picture and understand what we see, so we have this current I out, which is the cause of the magnetic field. That's the dot in the center is supposed to represent an outwards coming current. Put your thumb in the direction. Normally, what we've been doing is your thumb has been going up and your magnetic field or your fingers wrapping around in this way. Well, now point your thumb, get uh, that sort of thumbs up motion, and get your thumb to look right at you, and notice that your fingers will now curl around. So you have your thumb pointed right at you, and now your fingers will sort of curl around in this way. And so that's exactly what's happening in the picture. The magnetic field is a circular field around that wire. And we have a functional form of the strength of that magnetic field as it is generated by the current. We have a charge in purple moving towards the field, directly towards the wire, and that's going to will do some things for us in the equations that we use. So let's go back and make sure that we are looking at the right equations. Now this is the magnetic force equation. You don't want to forget this one. Uh, it's kind of the counterpart to the electric F E equals Q times E is the electric force generated by an electric field. Well, this is the magnetic force generated by a magnetic field, the B. And so this is just QVB sine theta, where Q is the charge, V is the speed of the charge, B is the magnetic field that it's moving in, and theta is the angle between the pathway, the velocity, and the magnetic field B. And the other thing to look at is that currents create magnetic fields with this equation B equals mu naught I over 2 pi r. And that's saying that if you have a current I, it's going to generate this sort of swirly magnetic field around the current that's going to get weaker as R gets bigger. And you can just plug in R, which is the direct distance from the current to the point that you're interested in. Let's say like point P or whatever. And I is, of course, the current value in amps. Mu naught is just a constant, which has units of Tesla meters per amps. And these are the two things that we need to really get this problem going. And so we can write down our equations that we are pretty sure we're going to need. FP equals QVB sine theta, QVB sine theta, and the magnetic field B coming from an infinite wire is mu naught I over 2 pi r. Now we want to look for anything we can use to simplify this problem, and I already see one thing right off the bat, this sine theta part. Well, that's the angle between the magnetic field and the velocity of the particle. The magnetic field is going around in this way. At the point where it meets the particle, you can see that the magnetic field is going to the left, while the particle has a velocity which is downwards. So v is down while b is to the left. If you put those together, these are forming a right angle. Okay? And so we can put in for our theta value, we can put in 90 degrees, and sine of 90 degrees is 1. This is as powerful as this magnetic force can be. If the angle was 0, that means that the magnetic field and the velocity were aligned, then that would be a sine of 0, which is 0, and there would be no magnetic force. Okay, and so let's double check that we have everything. So we're looking for the force. We do know the charge. That's 1 coulomb is the charge value going down. We know its velocity is 5 meters per second, or its speed. B, we don't know the magnetic field, but we can find it using this equation because it's coming from a wire. I is the current, 120 amps. Mu naught is a constant, and R is the distance from the wire here at the center to the point of interest, which is the location of the charge, which is the 0.3 meters. So we have everything. We just need to put it all together. That magnetic force is going to be equal to QV mu naught I over 2 pi r. And just to be clear, let's write out what each of these are. So 1 coulomb, the velocity is 5 meters per second. Mu naught is 4 pi times 10 to the minus 7 Tesla meters per amp. And the current is 120 amps, which is a huge current. You wouldn't want to be anywhere near that. And the denominator is 2 pi times 0.3 meters. We can take a quick look at our units and see what we get. Now Teslas are going to be a bit strange, but these amps cancel and these meters up there cancel. So we have a Tesla meter, a Coulomb Tesla meter per second. Well, Tesla, as it turns out, you can tell kind of from the first equation about the force, the units of Tesla are a Newton second per Coulomb meter. And we have, well, this meter cancels that meter. This second cancels that second. And then the coulombs cancels that coulomb. And we're left with just newtons, which is what we want to get that force on the left. And so at the end, we have, if you plug this into a calculator, looks like 4 times 10 to the minus 4, or 400 micronewtons, is the magnitude of the force. Doesn't seem like much, but for a small particle, it may be a lot, which isn't surprising considering that this is a huge 120 amp, and also 1 coulomb is actually a massive amount of charge as well. So a small particle would feel quite a large acceleration due to this force. Yeah, and so this is how you find the force on a moving charge due to a magnetic field created by a wire. A quick bonus question. What is the direction of that force? Well, we had already decided that the velocity of this positive particle is downwards and the magnetic field is to the left. And so you can use your right-hand rule number 1 to figure this out by pointing your thumb in the direction of velocity. So it's going to be a very bad finger. Your thumb is your V, it's pointing downwards. Your index finger is pointing to the left. And this is a lot like, this is the magnetic field. This is your B index finger pointing to the left, and that leaves your force pointing into the page. Is your third finger, your middle finger is pointing into the page. And so since this is a positive particle, that leaves that our force is into the page. We indicate that with an X in a circle.